The goal of this video is to review traditional seismic trace attributes and to illustrate their sensitivity to energy, bandwidth, phase, and thickness. For this purpose, we'll use a consistent set of simple half-space models and also some wedge models. Other than response phase, I don't use these attributes very often. The reason is they tend to be very sensitive to the source wavelet shape. There's been much that's been written about them in literature. For more information, a good place to start is the classic 1979 paper by Tanner et al. And also there's the John Bodine paper from 1984, Waveform Analysis with Seismic Attributes. These attributes fall into two main categories, instantaneous and response. Instantaneous attributes characterize sample-by-sample variability that makes up the seismic trace. They include real amplitude, quadrature amplitude, reflection strength, instantaneous phase, cosine of instantaneous phase, instantaneous frequency, and also 0 and 90-degree phase decomposition. Response attributes characterize simple reflection boundaries as well as complex reflection packets and zones. They do this by focusing on content on an energy envelope by energy envelope basis. Response attributes exhibit a blocky appearance because there is only one value that is obtained for each energy envelope lobe and is returned as a constant for the entire time width of that lobe, from trough to trough. Attributes in this category include response amplitude, response phase, response frequency, and response length. Turning to instantaneous attributes, first up is the quadrature. This is the imaginary part of the complex seismic trace and can be computed from the real trace via the Hilbert transform. Both the real trace and its quadrature counterpart share the same amplitude spectrum. The quadrature trace, however, is phase rotated by 90 degrees. Zero crossings on the real trace transform to peaks and troughs on the quadrature trace, and vice versa. The quadrature is used in various mathematical combinations to compute other complex trace attributes, such as, for example, response phase and instantaneous frequency. In terms of the sensitivity chart, it is sensitive to all three: energy, bandwidth, and phase. If the data is zero phase, zero crossings can represent tuned bed boundaries. Reflection strength, sometimes referred to as energy envelope, is defined as the total energy of the seismic trace. It is independent of phase, and its values are always greater than or equal to zero. Looking at the sensitivity chart, it is sensitive to energy and bandwidth, but it is not sensitive to phase. It can become helpful when working with datasets that exhibit uncertain or unknown phase. Strong energy reflections can be associated with major lithologic changes as well as fluid changes. Lateral energy variations can help quantify changes in rock properties and bed thickness. They can also be helpful for distinguishing massive reflectors from thin bed composites, and also in the case of unconformities, where reflection strength will vary as subcropping beds change. Instantaneous phase emphasizes spatial continuity or discontinuity of reflections by providing a way for weak and strong events to appear with equal strength. It does this by associating positions along the waveform to a phase value, and is often displayed using a wrapped color bar that represents plus or minus 180 degrees. It is sensitive to bandwidth and phase, but not energy in isolation. This makes instantaneous phase effective for bringing out weaker events. It can be effective at highlighting discontinuities, faults, pinch-outs, angularities, and bed interfaces. Seismic sequence boundaries, or sedimentary layer patterns, and regions of on-lap and off-lap patterns often exhibit extra clarity. Next up is the cosine of instantaneous phase, also called the carrier. It has the same uses as instantaneous phase, with one additional benefit. It is continually smooth time-wise. By avoiding the plus or minus 180 degree discontinuity that occurs with instantaneous phase, the cosine of instantaneous phase can be further processed, for example, filtered and stacked, using conventional seismic processing tools. Like instantaneous phase, it is sensitive to bandwidth and phase, but not energy in isolation. Amplitude peaks and troughs retain their positions, but with strong and weak events now exhibiting equal strength. Instantaneous frequency is the rate of change of instantaneous phase. It is a measure of time-dependent mean frequency. Tuning aside, it is sensitive to bandwidth, but not energy or phase. It can be helpful for looking at changes in thickness and rock or fluid properties. Since reflection events are often composed of multiple, closely spaced thin beds, the superposition of multiple reflections can produce an instantaneous frequency pattern that characterizes the composite reflection. Destructive interference caused by seismic processing artifacts, such as incorrect NMO or statics corrections prior to stacking, can artificially reduce the frequency content. 0 and 90-degree phase decompositions emphasize the 0 and 180-degree components, or the 90 and 270-degree components within the reflection data. Tuning aside, they are dependent on energy, bandwidth, and phase. Once tuning is introduced, they can help highlight resolved blocky events, which tend to exhibit 0 and 180-degree behavior, versus unresolved blocky events, which tend to exhibit 90 and 270-degree behavior. This, of course, relies on the input being zero phase. Additionally, uncertainty and complications creep in when you consider that the subsurface is made up of a much more complicated distribution of resolved, unresolved, blocky, and gradational content. Now let's turn to response attributes. These attributes characterize the content in each energy envelope lobe. First up is response amplitude. This is the amplitude of the reflection strength at the point at which the energy envelope is a maximum. One value is obtained for each energy lobe and is returned as a constant for the entire time width of that lobe from trough to trough. It is independent of phase and is useful for measuring energy variations from energy lobe to energy lobe. Like reflection strength, response amplitude can be sensitive to bed thickness as well as rock and fluid properties. However, because the response calculation returns just one value per energy envelope lobe, zones of interest encompassed by single energy lobes become characterized by single values that then are more easily mapped. Response phase is the value of instantaneous phase, once again at the point at which the envelope is a maximum. One value is obtained for each energy lobe and is returned as a constant for the entire time width of that lobe from trough to trough. This value commonly represents the dominant phase of the waveform. It is independent of amplitude and is particularly useful for discovering phase differences in overlap portions of seismic surveys. Sharp lateral changes can be indicative of detection to resolution transitions. I rarely turn to instantaneous and response attributes in day-to-day work, but when I do, it is typically response phase. This is a very useful attribute for investigating phase changes. Response frequency is the value of instantaneous frequency, once again at the point at which the envelope is a maximum. One value is obtained for each lobe and is returned, just as it is for the response phase and for the response amplitude, as a constant for the entire time width of that lobe from trough to trough. This is a measure of the dominant frequency of the waveform contained within the envelope, and is useful for measuring dominant frequency variations from energy lobe to energy lobe. It is independent of energy and phase. It emphasizes tuning characteristics and can help with characterization of composite tuned reflections. As a set, response amplitude, response phase, and response frequency describe the complementary dominant seismic characteristics within an energy envelope lobe. There are other response attributes, such as, for example, response length. Response length is the half-length of the energy envelope lobe from trough to trough. One value is obtained for each energy lobe and is returned as a constant for the entire time width of the lobe from trough to trough. It is independent of phase and amplitude. Complex reflection packets can have longer response lengths than simple reflections. This attribute provides a measure of seismic reflection stability and is therefore useful in characterizing the complexity of the seismic waveform encompassed by the energy lobe. If the response length is laterally stable, while the other response attributes are not, this can be an indication of waveform variability and can be caused by tuning rather than by poor signal or noise or unstable reflections. My goal here was to provide a brief intro to the traditional seismic attribute set. As I mentioned earlier, much has been written about these attributes in literature and online. And just once again to mention, for more information, I would recommend starting with the 1979 paper by Tanner et al., that is Complex Seismic Trace Analysis, or John Bodine's Waveform Analysis with Seismic Attributes.